All right, hello everyone. Now that we've uncovered a little bit about Alexander Hamilton's method for apportioning Congress and other resources, we can take a look at some other methods. Because his method, although logical, simple, easy to follow, and easy to implement, does have a few things that are a little different about it, a little unusual. And one of those things that happens, if you've noticed with some of the previous problems, is that it because larger states tend to have larger ranges of decimals, they are more likely to have larger decimals and therefore tend to be more likely to get the extra seats. So Hamilton's method does have a bias towards larger states or larger entities in general. Let's go back and let's take a look at this problem, right? And if you recall, we can now look at this under the lens of Hamilton's method. You can kind of see what I mean. So we did this one in the last video where we had 34 over 461 times 400 for Canada's representation, because we turn this into a ratio first, and then from this ratio we were able to turn it into a amount out of 400, and I believe the amount comes out to just over 29.5, so 29.5011. It was something like that. And then some of the other ones here, so Mexico ends up, it was like 98.9 something, and then USA was 271.58. Okay, so just kind of recapping some of those numbers, and the question is, when you add those together, when we round them, they're all higher than 0.5. So when we rounded them all, you ended up with 401, right? If we apply Hamilton's method, we do the opposite. We round everything down, and 271, and then we add these together, and this gives us 398. So with 398, we have 2 seats left over. Well, who is going to get those extra seats? According to Hamilton, the ones with the largest decimals, and that's Mexico and the USA, giving you a final total of 29, 99, and 272, and that certainly adds up to 400. But there's a major problem with this. And why are we taking away from Canada? Well, Canada, it's funny, that's the one that rounds down rather than up. Yet it's the one with the smallest representation. So here we have a case where we're losing, essentially, although it's not like a real representative, they're essentially losing half of a representative. Well, half of that is like, 2% of their representation. Whereas a place like Canada, where like the USA is losing less than 1/2 of 1%. So if Canada loses and rounds down, the difference between 30 and 29 is much more significant than the difference between 271 and 272. So even though this has a 0.58 on it, you can make a case that perhaps USA doesn't need the extra representation because it already has so much that this amount of people can essentially be like distributed among the 271 full groups without really changing anything, versus this, which has a bit of a bigger impact on the 29. So a couple people thought about this and wondered if there's a way that we can incorporate this into an apportionment method to ensure that places that are really small, do have a little bit of a higher chance of getting their representative back. So that leads us to, as we go through, we did all this, we did this, we're in Lowndes Method. Okay, this is a variant of Hamilton's method, which attacks the decimal problem a little bit of a different way. Excuse me. So here's the idea. Instead of rounding up the states that are the closest to receiving another seat. Instead, we're going to round up the ones by which that amount lost is the largest by proportion. So the idea here is that Hamilton's method, it goes by largest groups by count. And so Hamilton adds extra representatives to the largest group by count. Lowndes adds to the largest groups by proportion. In other words, that amount that's different from the whole number of seats. How big of a proportion is that? And the ones that tend to lose the greatest proportion, those are the ones that should go up rather than down. Now you can see right away how that might favor something with, a state with only one or two representatives. So like, for example, a state like Vermont, which only has one representative, you have a case where that rounds up to 2, and that's double the representation. Versus a state like California, which has 52, the difference between 52 and 53 is very, very small. Okay, so here's what we're going to have to do. This is going to be the same stuff as Hamilton's method, but with one extra calculation, and that's this idea called a relative fractional part. It's the fractional part of the natural quota divided by the integer part. And we're going to do that one first, after we do the natural quota. So the idea is then we compare that number rather than the original decimals. So what we can do is we can go through a problem with both Hamilton's and Lowndes' method, and you can see the difference between them. Sometimes they agree, sometimes they don't. Okay, so let's go through this problem here, right? We have the 1790 Delaware apportionment, 76 seats. Okay, so what we can do is, again, we have 76, we can come up with some totals. I'll remember always first have your total there. Now, in this case, I need a calculator, huh? All right, so let's pull up the calculator here. And although I'm guessing you guys can't see the calculator, 18,920 plus 19,686 plus 2488, 59,094. So this is the total of 59,094. Okay, the next thing we're going to do is we're going to divide by 76, and that will give us our divisor. So if I do that here, I do divide it by 76, 777.552 cents. Okay. So now, if you recall, for the natural quota, we are going to have our divide by 777, and then we'll have our initial allocation. Those are going to be the same in both of these methods. So let's just go ahead and do that now. We're going to divide. So what I'll do is I'll just put that in memory. Then we'll just do 18,920 divided by that number, 24,332. Okay. And then we'll just do the same for the others. 19,686 divided by the divisor, 25,317. And then finally, 20,488 divided by divisor, 26.349. With an initial allocation of 24, 25, 26, and when you add this up, you get 75. That means we've got one left to give. Okay, So we've got one left to give. Who's going to get it? Well, let's see. If this were Hamilton's method, under Hamilton's method, that's going to go to Sussex. I'm going to put an H. Okay. So now what we're going to do from Lowndes' method, and this is the part that's different, is we're going to do an extra division step. And that extra division step is going to look like this. Let's take the first one. And we'll be able to make a new column for this in a bit. I'm going to just kind of take this and kind of slide some of this over a little bit. Let's grab these numbers. Let's push that over. Let's call this in and then get these numbers and slide these over. Okay. And then finally, so I'm going to create a new column over here. And we're going to call this relative. Ooh, there we go. And then let's get rid of the underlying. Perfect. Okay. So we're going to create this relative column. And so the way that we do the relative column is we divide the decimal part by the integer part. So what I'm going to do is down here, because I don't have the calculator handy for the screen, so 0.3328 divided by 24. Okay, and I'm going to do that calculation, and that's going to get me 0.0139. What that number tells us is that this decimal that we drop to create our initial value, that represents 1.39% of the needed representation. So by dropping that off, we're losing 1.39%. Now that doesn't seem like a whole lot, but don't forget that these numbers here are very high in terms of the amount of seats, because this is actually a fairly large legislature for this particular type. Okay, let's do the next one. So we're going to do the same math, and we're going to get pretty similar results here. So 25, so 0.3179 divided by 21, and that's 0.0151. Okay, and then finally, we're going to do 0.3493 divided by 26, and that's 0.0134. Okay. Okay. Oh, I think I did that one wrong, the one before. So 0.3179 divided by 20. 0.0127. Okay, I made a slight mistake here. That's okay. This is 0.0127. Okay, 0.0127. So these ones represent approximately a little over 1% of the population. Now, this is really, really, really close. But which one's bigger? It looks like Kent has the bigger one. So in this particular case, it's Kent that gets the extra seat instead of Sussex. So under Hamilton's method, Sussex gets the extra seat with the highest decimal. But under Lowndes' method, Kent gets the extra seat. Now, what does that mean in terms of representation? So again, look what's happening. Hamilton is favoring the big one, and Kent is favoring the small one. Interesting how that seems to happen. So the difference here is with Hamilton's method, it's going to be 24, 25, 27. But if this were Lowndes' method, you'd end up with 25, 25, 26, which is, pretty close there. And which one do you like better for this situation? I guess it doesn't matter, does it? So, it could be personal preference, but this is now one of the things that we're going to deal with, is that there's different ways to look at fair, like what is fair in a population, um, in terms of assigning resources. Okay, so we did this and we figured out that different ones get different seats. So here's another case that can happen. So we have a Scandinavian Economic Council. And again, I'm going to do kind of a shortcut here. Here are the values. So the Scandinavian Economic Council has a 40-seat council. Okay. So the divisor for this is going to be 623.25. We're going to take 24,930 and we're going to divide by 40. And that's going to give us this number here. Okay. So what I'm going to do, let's move this up a bit. Actually, what I'll do is I'll just delete this in here, and I'll just write it better here. We'll just put it up here. And we'll do divisor equals 623? It was 623.25. Okay. D equals 623.25. Okay. Oh. So once again, we're going to look at this problem. And this problem also has a very unique outcome to it as well. So when we did this problem, we have these columns, but you might notice with these countries that Iceland has a way smaller population. And actually, because the divisor is bigger than its actual population, they get assigned a total of 0 at first. But you'd hope that they'd get 1 that get rounded up, but it turns out they don't. And in this particular case, when you do the natural quotas for this, you end up with an initial value of 0, and then there are under Hamilton's method, these 3 get the extra seats. There's 37 that are assigned, 3 extra seats, and they go to these 3. That's really interesting, because that's probably not something that you might have expected. You might expect the 0 to get 1. But remember what we said before, Hamilton's favors larger states. Just, it's not always understood why. You'd think that just dividing by this number, when you're dividing by that number, you have as equal chance to be at any decimal as anything else. But it always seems to favor larger ones. So what winds up happening is you end up with situations like this where you get a 0. Now, other parliaments, other places in Europe, like this here, when they use Hamilton's method, and a lot do, in their legislatures, they use Hamilton's method to apportion seats based on voting totals. So with voting totals, you actually want this to happen, because by having a 0 there, there's like a minimum population that needs to happen in order to earn that first seat. And under Hamilton's method, in this case, it's going to end up being like, what is it here? It's not even here. It's a little about 3%. This is roughly 3% of this entire population. Maybe a little bit, no. I'd say more like 1.5%, 2%. The minimum usually needed in Hamilton's method to get that first seat is right around 5%. Once you have about 5% of the overall group, then you are much more likely to get a seat. And in this particular case, with the total being 24,930, and the divisor being that, as long as you are like starting to get close to that divisor, so like I would get closer to, if this were closer to like 600, then yes, you're going to pick up the extra seat. So 5% is a usual rough estimate by which at what point you Hamilton's method will get you that representative. Lowndes method's a little bit different. So when you do this, right? Okay, when you do a problem like this under Lowndes method, let's do Iceland's rule. Iceland is 313 divided by 6, 23, 25. You get 0.5022. Okay, which is why you get the 0. So one of the things here, if you were to apply Lowndes method to this, the calculation you're going to have to do is 0.5022 divided by 0, which guess what? Doesn't exist. When that happens, because under Lowndes method, okay, that division doesn't exist. So how do you think of it? Well, consider it this way. How much representation is lost by rounding down? All of it. So when we do Lowndes method on this data, okay, we're going to take the division when you divide by 0. Because division by 0 doesn't really exist, it's more like an arbitrarily high number. We're going to consider zeros as automatically gaining one. And the US Constitution actually has this provision in it that should a state have a representation of 0, then they automatically get the first representative. And Lowndes' method does that automatically for us. That provision is built in. So now if we go do some of the rest of these, if we do 4707 divided by 623.25, we get 7.5523. We get 9104 divided by that, 14.6073. Let's do Denmark. 8.8937. Let's see. 8.8937. And then Finland will be a little bit smaller. 8.4 repeated. Okay. So now that we have those, in this method, Lowndes is going to get the first nod simply because they have the 0. So they're going to get a guaranteed representative. That's what makes this method enticing to use, but this was actually never used by the US government. All right, so which ones under Lowndes' method are going to get the extra seats? Denmark is going to get the extra seat under Lowndes' method. And the other one that's going to get the extra seat is going to be Norway. .5523 divided by 7 is bigger than all the others. Okay, so Lowndes' method has a single difference in that Sweden gives up one of its representatives to go to Iceland. But look at the chart. Sweden already has 14. Doesn't that make sense? So Lowndes actually is a lot more fair to smaller states, smaller populations. Okay? And so that's a little bit of the understanding of Lowndes' method and how it is the same and different from Hamilton's method. Both methods are what we call rounding methods, or I forget there's a term for it. Because the other ones are divisor methods. Oh, this one's quota methods. We call these the quota methods because they're based on adjusting quotas as need be. Um, the other thought that we're going to have from this is something called a divisor method. And so we're going to do those next time. Okay? All right. I hope this was kind of a nice little explanation, kind of goes through the math that you need to do. So I hope you have a good night. Take care.